Our next presentation, State of the Science for Foreign Material Detection. Our presenter is Olga Pawluczyk. She is the co-founder and CEO of P&P Optica based in Waterloo, Ontario. Olga is an expert in medical imaging with a technical background in systems engineering and deep knowledge of the science of spectroscopy. Under the leadership of Olga and her co-founder, her father, Romek Pawluczyk, PPO launched in 2004 as a research company focused on developing high-end spectrometers. Olga assumed full leadership of the company in 2010 and has grown the company from a research-driven organization to focus on commercialization across different industries, oil and gas, space exploration, and medical applications. Olga pivoted the company over the past 6 years to focus exclusively on building quality and safety solutions for the food processing industry. Olga, welcome, and you can start sharing your screen now.
Thank you very much, Joe. I believe this will work. Hello, everyone. I'm very happy to be here and have the opportunity to speak with you. I think the FSIS talk there was a question towards the end about foreign object detection. So that's the area that I would like to discuss a little bit more with you. And as a person who's been doing medical imaging and imaging for most of my career, I hope that it will give you a little bit of a perspective of how the companies that actually make detection systems think about detection, and maybe help you in your thought processes as you decide to implement some new methodology of figuring out how to detect foreign objects or even inspection methods. I hope that you will have some questions for me towards the end, but really this is meant to be as a bit of a tutorial about how to think about detection systems. So the one thing that we often find is customers come and ask us, can you detect foreign objects? And this is true for any type of imaging or detection system. Most of us can say, yes, we do. The problem is, what does it mean actually to detect? So if you consider something like an event that has two outcomes, so for example, presence of foreign contaminant or a medical condition, these days COVID testing seems to come to mind really quickly, or even presence of great quality product versus everything else. It is very important to understand the terminology that we use. So we assume that something is true, so it's positive or negative. Actually, when you introduce an inspection system, no system can actually work perfectly. So what we have is options that don't just fall in true or false. There is something that might be true that's not actually true, or false and it's not actually false. So for example, a false positive test on COVID or a false positive on finding a foreign object, which would essentially trigger a rejection of perfectly fine product. So it's important to keep in mind that there is such thing as false positives or false detections, and that in any system, there is just zero possibility of detecting 100% of whatever is ailing your production. So there is no silver bullet to 100% detection of foreign materials or 100% detection of any issue in food production. And that's unfortunately true for any detection of any type, whether it's chemical or vision, like what I'll be talking about. The other aspect is that comparison of detection systems is very difficult because typical studies only address the true positive counts. So you say something is detected, so true positive COVID test, and you can check it over and over and over again. And when every single test that you perform gives you a positive result, or you can actually physically inspect something and touch it, you know that you found the truth. However, you don't know what you have missed ever. So there's no, unless you have an additional detection modality that allows you to catch things that you are not able to catch, there is really no way of finding false negatives or rejections, or essentially detection of something of a true something that actually happens. And then human factors inevitably come into play during detection. Humans are terrible detection mechanism, and we use them in food production very often. It's kind of the fail-safe method of looking at foreign objects or detection of other issues on the food production line. And the problem with humans is that we just don't pay attention very well. So when we start on a task, we pay a little bit more attention, but as the task progresses, it's very easy to stop paying attention. So even though I always hear the stories of people going, well, our human inspectors can find the smallest speck of foreign object, the problem is the same humans can miss a big shovel going through the production. And I'm sure that many of you have seen and heard those horror stories. So not only do we have to look at humans as inspectors, and I think that's a very valid way of using human inspectors in food production, but we also have to make sure that we supplement their ability to concentrate and to inspect with other technologies. So let's kind of step back a little bit and talk a little bit about what it means to detect something. And again, whether it's a human eyes or any other detection method, it's really important to understand that detection doesn't mean you will see 100% of any size object all the time. So what can we actually reliably detect is the question that I would encourage you to ask on your production lines. And is it, are humans reliably going to detect things as small as 1 millimeter or 5 millimeters or shovels? And oftentimes the minimum detectable object is actually not what you're looking for. You're looking for the proportion of time or how many of those small objects will your inspection methodology actually find. So I'm showing here something that we call a detection curve, and essentially it shows the percentage, probability percentage of catching something of a different size, and looking at a comparison of several detectors. The other aspect to think about is the language that we often use for detection is quite imprecise. So what does it mean to have the smallest pixel size? Will you actually detect an object that's as small as the pixel, or will it depend on other aspects? And actually, typical resolution and ability to find objects that is determined by things that have nothing to do with detectors, but also the noise of the facility, how the system is configured and maintained. And really, a lot of it happens on the back end of software procedures and software algorithms that try to extract this very complex information and measure a detection. So when looking at detection choosing a detection model, it's really important to think about detection curves and also thinking about what is this system good at and what other system I might need or my other detection method I might want to implement to really help with detection of the things that are important to me. This is a little bit simpler for grading of quality, where you can have a better threshold set. So The other aspect that we always try to pay a lot of attention to is what I mentioned earlier, is the false positives. So, there is one type of a perfect detection system, and it's a system that rejects 100% of your product. Essentially, you have 100% certainty that you have rejected every single foreign object. But again, we live in a real world. So it's how many false positives occur. So how many times do we reject good product that has no foreign materials, um, as we try to turn up the ability to find as many foreign materials as possible. So again, that false positive aspect, or how much do we reject of a good product, is quite important in thinking about detection systems. And a lot of people quote this as how many pixels do we mislabel? And again, pixel does not equal the amount of food that you actually reject from your processing line. So if we kind of step back and look at what are the ways of detecting things, most detection methods use some sort of electromagnetic wave, from microwaves to UV light to X-rays. And then there are some more complex methodologies like magnetic resonance imaging or CT scanning, where not only are we detecting some signal from the product, but we're also doing a lot of computer analysis to figure out what we're seeing actually. Right now in food inspection, really we're concentrating mostly on on vision systems of some sort. So whether it's an X-ray or visible light or infrared light, we tend to use vision systems. And again, human inspectors are a perfect example of that, where we use human eyeballs vision to determine if there are foreign objects in our stream. Some technologies have been really well applied to the food industry. So for example, X-ray systems are fantastic for automation of inspection. They allow one to find foreign objects throughout the entire volume of the product. X-rays can penetrate through most products and most packaging. Definitely meat is very easy for X-rays to observe. There are many sources, many companies that build X-rays. The safety aspect is also very well taken care of, but the problem is that X-rays differentiate foreign objects only on the density of that object. So the rule of thumb is that anything that is able to float in water is going to be very difficult to detect by X-rays. And the other aspect is the product should be relatively uniform. So if you have a low density, fatty meat going on your operation most of the time, but at some point you start looking at very dense muscles with bones in, the same X-ray system will have hard time detecting identical foreign objects in those two types of material. So it's important to understand what your X-ray system is set for, and really pay attention to what kind of product you're looking at, the uniformity, how you present the product, thickness variability, and so forth. And a lot of X-ray work, even with dual energy and so forth, really can't distinguish chemistry. It just sees density. So most metals, for example, will look very similar to an X-ray. Calcified bones might be detectable, yet less calcified bones will just pass through and look like the meat that's on the line. Another method often used in inspection for foreign objects is metal detectors. They are less imaging and more detection, so they tell you that in this volume of product, we found something that is metal. And these machines tend to be very good at finding iron-based metals. But other things like aluminum, for example, or some stainless steels will not be easily detectable. What's nice is that this method also sees through packaging, also looks at a volume, and can see a very small objects, as small as 0.8 millimeters in many of the literature and systems that are available right now. The problem, again, is how do we present materials to it? And if you have very uniform thickness, very uniform type of meat coming on your production line, these small sizes are quite easy to detect, but only of metals. The other issues are when we're talking about further processed food, where you're starting to add other ingredients like salt, for example. Some of that can really mess up the signal from metal detectors. So this is really better on kind of earlier in the value chain and pre-processing inspection of product. Now, coming to kind of my bread and butter, vision systems, these are now available on the market, and they really try to replicate human inspection, but with standard cameras. You know, a lot of industrial applications are using vision systems already, so it was a logical step to go into the food industry. The problem with vision systems is that meat processing, or any food processing, as a matter of fact, is very complex. The materials are very non-uniform. So it's very easy to see a scratch on on millions of iPhone screens, but it's very difficult to actually see specks of foreign objects on that complex, you know, background of ground meat, for example. So food, because it varies so much, and meat, because it varies so much, actually reduces the contrast for imaging systems, and it's very difficult to catch smaller products and so forth using just standard cameras. So imagine just looking for, you know, when you drop a coin, it's much easier to find it on a white tile floor than it is to find it on a patterned carpet. Same principle applies to pretty much any vision system. So how people have tried to approach this is, instead of looking at just 3 colors from a camera, could we look at multiple colors or multiple spectral bands, and now start seeing more differentiation in composition based on color interaction. So multispectral systems have also been entering the market, and right now most applications happen in the produce and kind of fruit sorting, but we're starting to see these approaches entering the meat industry as well. And unlike cameras, because we're seeing now multiple colors, we can really start differentiating more information per pixel of image, and therefore we can see more differentiation between background or the meat product versus foreign objects. Now, the problem here is complexity increases in calculations and whatnot. So can we match the speed of your production line? And finally, this is something that PNP, my company, has built out, is using hyperspectral imaging. And what's the difference here? It's, instead of looking at 10 or 30 bands of color, we're looking at hundreds of colors, and we try to differentiate things really based on chemistry. So to give you an idea, this is an image of a couple of bacon slices. And as you can see, there are several foreign objects included on this bacon. And actually, there are 8 foreign objects included. And if you see 6, you're as good as any vision system. But unfortunately, you know, X-rays wouldn't have found any of these products. They're all floating in water. Metal detectors wouldn't find these, and the human inspectors or color cameras wouldn't find these. What we are introducing is ability to chemically image products. So not only did we find the foreign objects, but we can identify them. And this is, I think, kind of the biggest new development in finding foreign objects in food production is chemical imaging. To give you some more examples, this is a couple of foreign objects placed on chicken nuggets. And a standard camera system would see 3 colors. So what camera sees and what you see are almost identical. And we can differentiate colors fairly well. But what if we look at those multiple color bands? So our eyes are miniature spectrometers. Essentially, as light falls onto something, the light is either absorbed or reflected by molecular bonds. And then based on knowing what light we shone on something, and then what we collected, we can actually predict chemistry of food objects. So you saw the camera, but now in multispectral image, we will see, in this case, 5 colors. It will give us a better differentiation of foreign objects. But what if you could look at all colors in the band that cameras see, or maybe in near infrared? So this is now a spectral image where every pixel has, in this case, about 1,000 wavelengths that describe very precisely its chemistry. So not only we see dye colors, for example, so whether it's blue plastic or white plastic, but we can actually differentiate what type of plastic we're seeing. So, rubber gloves, blue, and conveyor belt material, blue. To a camera system, they would look identical. To a hyperspectral system, they will look completely different. So this just summarizes a little bit the differences between the typical vision, multispectral, and hyperspectral imaging. With probably the biggest differentiations here is that the amount of information collected in hyperspectral systems is huge. So till very recently, they couldn't really match process speed. And this is when we're starting to see more and more companies developing hyperspectral imaging, allowing analysis so fast that you can actually reject foreign objects online at line speed. The other aspect is hyperspectral imaging, because it sees chemistry, is very good at finding foreign objects that don't belong, but might not have been used to train the system. So unlike X-rays, where you really know exactly what kind of object you can see, or vision systems, exact colors you can see, here, if something looks chemically different enough from your product, you can actually choose to reject it, regardless of whether you understand what that product, foreign object is, or what history it has. So to talk a little bit about what P&P has built, we actually have a system that allows us to look on the surface of products. And because we are surface analysis, just like human eyes or cameras, we flip products so we can see as much of the product as possible. The system by now has been delivered to several companies where we're inspecting things like pre-processed chicken parts and pork and some beef. And not only do we see, can we inspect foreign objects, but because we're seeing chemistry, we can even provide some information about composition or even quality. Just another couple of shots. But really, it's how do we implement this really high-end technology that's really has been laboratory based? How can we put it into a machine that can survive the rigorous requirements of production lines? How do we wash down an optical spectrometer, for example? So some of those problems were quite difficult to solve, but we were able to resolve some of these issues. So to give you a bit more background, things like detecting bone on chicken, again, chemically, this is very different looking object, so we can very easily differentiate it. Or finding something as small as an, under 2 millimeter white piece of plastic on white background bacon bits at line speeds. Again, contrast-wise, vision or human inspection would have extreme difficulties finding something this low contrast. And instead, with hyperspectral imaging, we can not only detect it, but even identify what type of material this is. The other aspect people often ask about is, well, okay, this is a surface-only methodology. So how likely are we going to find foreign object that's located underneath or inside of a product? And obviously, inside of a product, we would not be able to detect anything. But because we're a lot of hyperspectral and multispectral systems have more than one imaging head, we jostle the product, whether we flip it or jostle it in some way, in such a way that from probabilistic approach, we do detect most of the foreign objects. And again, a lot of the times, if it's a single foreign object, as the FSIS gentleman said, sometimes you can't deal with it. But really what we're looking for in foreign object detection is systemic issues. And when you see more than one or two foreign objects within minutes of each other, you obviously have a problem online. The other interesting aspect of hyperspectral imaging and chemical imaging is that, again, we can see quality. So for example, in this work, we were able to learn from human inspectors exactly how they perceive a great piece of pork, in this case, a pork loin. And then the system was able to duplicate the behavior of the best human inspector. Not going on sick leave and paying attention 100% of the time and looking at every single pork loin in the processing plant touch-free. This is an example where hyperspectral allows us to measure composition of pork fat. And you will see that there is actually, we don't just see surface. Obviously, light penetrates through some layers of meat and fat. So we do have almost a global kind of measurement of fat distribution through a product. This is one of the more interesting work that we've done recently. It's on detecting of woodiness of chicken breasts. And again, because we're seeing chemistry, we're able to see the differences in the protein in woody breast as well as water content, and are able to predict if a product is woody or not, and allow our customer to sort it out from the production line, where they can now use that woody breast in a product that will not be directly interacting with the consumer. So overall, I guess the gist of this presentation is to provide you with a little bit more idea how to think about detection. There is no perfect modality. What we're starting to see more and more customers and processors are using multi-prong approach, where they will have X-ray metal detectors and now more and more vision systems and hyperspectral imaging to find foreign objects. But as these systems are maturing and as technology is maturing, other things are possible as well. So that real-time identification of quality and composition on top of foreign object detection really can help in optimizing your production. So I hope that this was somewhat educational. If you have any additional questions, I'd be happy to answer, but here are some resources on our website. If you'd like to learn more, I'd be happy to answer those questions.
Thank you, Olga. We do have a few, just a couple of questions here for you. This has been a very amazing and very educational presentation, and we really, really appreciate it. The first question is, how practical are some of these technologies for smaller processors?
Yeah, that's a great question. It really depends on the volumes produced on a line. What we're starting to see is the ROI is pretty immense, especially if you're able to apply several of these. Foreign object detection, let's face it, is really an insurance process. So you don't have a recall or you're throwing out a little bit less product when you detect foreign objects earlier. If you can now start measuring composition and quality, it allows you to differentiate your product from the general market a little bit more. You can start providing a higher quality product, and then the ROI is much better. These are not unlike metal detectors, which run in tens of thousands of dollars. This is kind of hundreds of thousands of dollars, similar to X-ray machines. Practically speaking, we have seen this implemented by smaller processors as well, especially when they want to show and differentiate themselves by quality.
And our last question, can you give us an update on holographic ultrasound as a potential foreign material detection system?
A lot of the issues with ultrasound is that you do have to have a contact with the transducer. So that's where a lot of kind of traditional medical imaging approaches to foreign object detection, I think, do fail. You're introducing yet another point of contact with your product, yet another risk of contamination by using probe over and over again. So I think in some respects, maybe through a package or something like that, it could work. But I would worry about cross-contamination. That's why I think X-rays and vision has been such a more natural adoption curve. Again, it's non-contact.
Thank you, Olga. That rounds out our questions for today. We really appreciate having you, and your presentation was very informative, and I know that our listeners learned a lot from it. So we really thank you for being on with us today.
Thank you so much, and I look forward to any conversations we may have after. So thank you all.
Thank you.